video, we're going to take a look at the acid-catalyzed hydrolysis of a nitrile. So the general formula for a nitrile is this. So you have a carbon with a triple bond to nitrogen. And so this is a carboxylic acid derivative. Even though it doesn't quite look like our other carboxylic acid derivatives, but it still has a carbon that has 3 bonds to an electronegative group. And so it is a carboxylic acid derivative. And so all carboxylic acid derivatives can be hydrolyzed to give you the carboxylic acid. And so like amides, which we saw previously, this is going to require some forcing conditions. So we would do this with some aqueous acid and heat. So I'm going to say H3O plus and heat. And so that H3O plus solution is probably coming from something like HCl that's aqueous. And so predicting this product is not quite as straightforward as what we saw for our other carboxylic acid derivatives, where we're easily able to see our leaving group. So what it might be good to do here is to keep track of which carbon is kind of the carbonyl equivalent. So that would be this carbon here. So this is the carbon that you're turning into a carboxylic acid. So if you do this hydrolysis, you end up with the carboxylic acid, and the carbon of the carboxylic acid was the carbon of the nitrile. So if you remember that, that can help you to keep track of things. And if you're wondering what happens to the nitrogen, ultimately this is going to become an ammonium salt. So you would have that as NH4 plus, and the counter ion would be whatever counter ion came along with your aqueous acid. So if you use HCl, this would be ammonium chloride. All right, so let's take a look at a specific example. All right, I'm actually going to add an extra step to this example. I'm going to make my nitrile first, and then I'll do the hydrolysis. Because I want to remind you of a reaction that we saw in the first semester class. So if you had something like a primary alkyl halide and you treated that with sodium cyanide, you could do very easily the SN2 reaction. So this is a really good way to make a nitrile. So you could do an SN2 reaction on an appropriate alkyl halide. So if it's SN2, your alkyl halide just can't be too hindered. So it could be just a methyl halide, it could be primary, or it could be secondary. All right, so this is going to give us a nitrile. So we've got a carbon-nitrogen triple bond. So we've actually extended that carbon chain by 1 carbon. And then if we do this hydrolysis, so H3O plus and heat, remember we want to keep an eye on that nitrile carbon, because that carbon is the carbonyl equivalent. That's what's going to become your carboxylic acid. So when you're going to draw the product, so you've got that 1 carbon atom that was there, and then we added 1 more carbon atom. Here it is, and we will make that into the carboxylic acid. All right, and if you're focused on the major organic product, you're probably just going to draw that, and you're not going to worry about drawing the ammonium salt. All right, so this mechanism is extremely long, so we're going to do part of it, because essentially we get halfway through the mechanism and we end up with something that's a protonated amide, and then the rest of the mechanism is essentially just acid-catalyzed amide hydrolysis, which was covered in a previous video. So we are going to look at the partial mechanism here, and we will make a note of where to find the rest if you really feel like writing out every single step. And so I'm just looking at the mechanism for this hydrolysis, right? We know the mechanism for SN2 plus, I showed the arrows there. So let's take a look at this nitrile. Okay, and so we called this carbon the carbonyl equivalent, right? And that's because it's in the same oxidation state, being a carbon with 3 bonds to an electronegative atom. That puts it in the oxidation state of +3. So if we're calling this the carbonyl equivalent, whenever we did these reactions in acid, the first thing we saw was we protonated the carbonyl oxygen. We don't have a carbonyl oxygen, but we do have a nitrogen. So the very first step is you're going to protonate that nitrogen. So if you have H3O plus, so if we're in aqueous solution, we have lots our aqueous acid solution, we have lots of H3O plus and we have lots of water that can act as the base. All right, so we protonate this first. And then we can attack that carbon that we have called the carbonyl equivalent. So we've got this protonated, right? And so just like we saw with all of our other acid catalyzed hydrolysis, we're using H3O plus as the water and we're using, or H3O plus as the acid, and we're using water as the base and the nucleophile. So the nucleophile here is going to be water. So it's going to attack this carbon that we keep calling the carbonyl equivalent. And it's going to attack it the exact same way that you would attack a carbonyl. So there you have it. And so we can draw the product of that. So this carbon still has a double bond to nitrogen, which has a bond to hydrogen and a lone pair, so that's now neutral. And we have added a water. So now it might be a little bit easier to picture how this becomes a carboxylic acid, right? Maybe you can picture this becoming a carbonyl and this being the OH. All right, but we do have a lot of steps. We got to have this nitrogen be a leaving group, which means we want to get this protonated. So we need to take the proton off of this oxygen first. And that's because we're in acidic solution, but not that acidic. So we're not going to have two positive charges on this molecule. So those electrons are going to the oxygen. And so now we have a neutral species. And so now we can protonate this nitrogen. So we can protonate this with another equivalent of H3O plus. I say another equivalent, but really it is catalytic, right? We use some H3O plus there, we regenerated here. Overall, we don't change the concentration of H3O plus. So I'm going to protonate this nitrogen and draw what we have. And so we're going to have this carbon with a double bond to the nitrogen. The nitrogen has two hydrogens, so it has a positive charge. And we have OH here. Okay, so you might not really realize this, but if you draw the resonance structure, let's draw the resonance structure of this molecule. Here's where we mentioned earlier, the mechanism basically changes from, you get to a point where you've got what looks like a protonated amide, and that's what we have here. So if I kind of redraw this, you'll be able to see it. So we have, so that carbon there has a double bond to oxygen, right? We're forming it there. It still has a hydrogen attached, right? And then we have NH2, right? So at this point, right, you basically have something that is a protonated amide. So I'm going to do the same thing your textbook does and tell you that there are several steps in between here. But then I'm also going to note that those several steps are essentially the acid-catalyzed hydrolysis of an amide. So you can look at it. You're not going to have to reproduce this entire mechanism. The key thing is going to be able to recognize what you have going on here, and that if you have a nitrile, you're hydrolyzing it to give you a carboxylic acid.